Now I know what you're thinking. You're saying the integral test? You told us that we were doing series now. You told us that integrals were behind us. You have lied to us.
Honey, you're just being really loud. I'm just going to close the door, okay?
All right. So we've seen that a sequence and a function are related, as are a series and an improper integral. And the relation between a sequence and a function is that if I have some function, then the sequence is just considering the function evaluated at the positive integers, 1, 2, 3, 4, 5, and so on. And we can do something kind of similar when it comes to series. If I think about a series as a sum of different numbers, I can actually think of them as a sum of different rectangles that have height the number and width 1. So for instance, I can think of this as being a height of whatever that value is and a width of 1. A height of whatever that value is and a width of 1. A height of whatever that value is and a width of 1, and so on down the line. So in other words, the series that I have can be thought of as an approximation of an integral, which is the area under a particular curve. And in particular, if we're interested in infinite series, which is what we're studying in this course, then we have to be interested in the area under a curve where we're considering the integral to go from the value of 1 all the way to infinity. So in other words, the integral from 1 to infinity of f of x dx is kind of like, I'll sort of put an approximation sign, it's kind of like the series from n equals 1 to infinity of an for the specific case of an just being equal to the function f evaluated at the point n. So we're able to relate the underlying sequence an to the function, and then we're able to relate the series, the sum of all of the an's, to this particular improper integral. Now, we have this nice picture, but I want to be able to formalize it in a theorem because we've studied improper integrals a ton in this course. We've figured out, for instance, how we can determine whether an improper integral is going to converge or diverge. And if it converges, we can figure out what it converges to. Indeed, this is our formal statement here. If our function obeys a bunch of properties, we'll talk about in a moment, then if you have that the integral converges, you get that the series converges, and if you get that the integral diverges, then you get that the series is going to diverge. So in other words, this really strong relationship between what the improper integral does and what the series does. This can be stated in a couple different ways. First of all, the positive and decreasing part works exactly the same thing as its negative and increasing. Doesn't particularly matter. So positive and decreasing or negative and increasing, those paired together. It also doesn't particularly matter that we start at the 1 here. If you think about a series, whether a series convergence is like a long-term question, a question then goes to infinity. If it bounces around and isn't well behaved for the first 100 terms or first million terms, it doesn't really matter. So we could, for instance, start this at some value of a, and then our integrals would start at a, and our sum would start at the, maybe not a exactly, but at least some integer around a. And indeed, it doesn't really matter what happens. So we can deal it. If our function has some discontinuity at 3, that's okay. We'll just start later than that. But conventionally, we usually are going to write starting from 1, unless we have some strong reason why we don't want to do that. These 3 conditions, continuous, positive, and decreasing, it's important to have them all, because something can happen with integration that doesn't necessarily happen with series. For instance, imagine you had this weird function where it did something weird, and maybe it diverged, but that precisely at the integers, right? F of 1, f of 2, f of 3, it was discontinuous. It did something completely different. Say it was all zeros. F of 1, f of 2, f of 3 was all zeros, but the rest of the function was really large, and so the integral under its area would diverge. But then the series, because the series is only built out of the f of 1, the f2, the f3, then that thing would converge if you made them all 0. So you need to have it continuous so you don't have any weird holes. Likewise with the positive and decreasing pairing here. If your function has portions where it decreases, maybe it even dips beneath the axis, you could be subtracting stuff in the function, but you wouldn't be perceiving that in the series. So you need to have all of these different conditions being true, and then you're going to get this nice result for the comparison between an improper integral and a series. A very important class of series that we're going to study now are referred to as p-series. And they are 1 divided by n, where n's are variable, all raised to the power of p. And in some sense, they're the opposite of what we studied before. So previously, we studied the geometric series. And in this case, it was some sum from usually 0 in that case to infinity, but whether it started at 1 or infinity doesn't really matter. And you would have a constant, then you would have a ratio to the power of n, an r to the power of n. So it was the exponent that was changing, and the ratio was fixed. A p-series is exactly the opposite. The exponent is fixed, and it's the ratio which is now changing. So geometric series and p-series are in some sense opposite. They're both a ratio to some power, but whether it's the ratio or whether it's the power that changes is different between these two different examples. Speeding through that review, it was that if p was less than or equal to 1, it diverged, and that if p was greater than 1, it was going to converge. And so what we get is, by the integral test, the same is true for p-series. So by the integral test, the p-series, the n equals 1 to infinity of 1 divided by n over p, converges for p greater than 1, and it diverges for p being less than or equal to 1. Now these p-series are going to be tremendously important to us. We're going to compare all sorts of other series to p-series, just kind of like we compared a whole bunch of other messy improper integrals to the p integral. And so it's really good that we have this nice answer given to us by the integral test. 2 points to keep in mind. First of all, we're not claiming that the value of an improper integral and the value of a series are the same value. We're only saying if one converges, then the other converges. Indeed, as we saw from our pictures, they are a little bit different, right? The right approximation using delta x equal to 1 is not the exact same thing as the area under the curve. So yes, if they both converge, they converge to two different values. The point is, if the one converges, so too must the other. Secondly, it's really important to make sure that these conditions are actually verified, that it is continuous, that it is positive, that it is decreasing, or alternatively, continuous, negative, and increasing. If it is not the case that you have one of these properties, it's very easy to make a mistake by trying to go and look at the integral. It has to have these properties.